Okay, in this video, we're going to explore the first of several what we call trig identities. And all trig identities are trig formulas that just happen to be true relationships between trig functions. We've already seen one when we talked about the tangent function being sine over cosine. That's an example of a trig identity. So there's a lot of trig identities. We'll explore a few of them, starting with arguably the most important trig identity. And so we're going to talk about that first. So let's evaluate this expression sine squared theta plus cosine squared theta for two different angles. And just a note here, when I say sine squared theta, that might be notation that's a little bit different. It's really just shorthand notation for taking the sine of an angle and then squaring the answer. So rather than putting parentheses and putting the square, we just put the square in between the sine and the theta, and we read that as sine squared theta, but it really means the same as this. So for pi over 3, we're going to take the sine of pi over 3, square that, plus the cosine of pi over 3, and square that. Pi over 3 is a special angle. So if you've been following along, you know we can use the triangle to evaluate the sine and cosine of pi over 3. Hopefully you're getting good at reconstructing this triangle. For pi over 3, then the opposite side is root 3. Hypotenuse is 2. This is 1. Sine of pi over 3 is opposite over hypotenuse. So I get root 3 over 2 squared. Cosine is adjacent over hypotenuse, 1/2 squared. Root 3 over 2 squared is root 3 times root 3 is 3. 2 times 2 is 4. So that's 3/4 plus 1/4 gives me 4/4 or just 1. So it turns out for theta equals pi over 3, sine squared of pi over 3 plus cosine squared of pi over 3 adds up to 1. Let's see what happens if we use a different angle, like pi. So we want to do the sine. Now I'll write it in this notation. Sine squared of pi plus cosine squared of pi. Now for pi, recall this was another thing we were discussing. If you have an angle like pi that puts you on one of the axes, you can think about the unit circle. And at pi, the coordinate of this point, if this was a circle of radius 1, would be -1, 0. The sine of pi is literally the y-coordinate, so you'd have 0 squared. Cosine of pi is the x-coordinate plus -1 squared. And that also gives me a sum of 1. So you're probably suspecting now, since I've shown it for two different angles, that sine squared of theta plus cosine squared of theta will always give you 1. And in fact, it does. One way we can really prove that that's always going to work is if I go back to my, really it doesn't have to be a unit circle, but if I put a random triangle inside my circle, call this angle theta, and let's say I label this side x, this y, this r. Let's see what happens if I do sine squared of theta plus cosine squared of theta. The sine is opposite over hypotenuse, so I'd get y over r squared. Cosine is adjacent over hypotenuse, x over r squared. This is y squared over r squared plus x squared over r squared. I have the same denominator, so I could just write this as y squared plus x squared over r squared. But it's pretty easy to see that the numerator, y squared plus x squared, that's just like doing the Pythagorean theorem. Y squared plus x squared should equal r squared because it's a right triangle. So that gives me r squared over r squared, which is always going to be 1. So in fact, this proves this identity. This is always true. And this is you got to know this. If you're going to do stuff with trig, you have to be familiar with this identity. Shows up everywhere. For any angle theta, not just special angles that I showed up there, sine squared of theta plus cosine squared of theta will always give us 1. This particular identity is known as the Pythagorean identity. Probably guess why, since we use the Pythagorean theorem to justify this becoming r squared. And once you know this identity, there's two offshoots from that are also very useful. If I take this identity and let's say I subtract sine squared from both sides, I move it over here, that would leave me with just cosine squared equals 1 minus sine squared. This is 1 minus sine squared equals cosine squared theta. And alternatively, if I took this identity and subtracted cosine squared to the right side, I would have 1 minus cosine squared would equal sine squared of theta. As I said, there are more identities that we will be discussing, but what I want to do first is show you, give you an example of why these identities are very, very useful. For those of you going on into calculus, it's very, very common in calculus. You work with trig functions there and you do some calculus math with trig functions. And what sometimes happens is you do a problem and you end up with this, something like this as your answer. Now, let's say you had access to the answers. Let's say it was an odd numbered problem and you knew the answer was in the back of the book. So you get this as your answer and you look in the back of the book and they have something that looks completely different. So the natural reaction is you're going to think that you did something wrong when in fact, your answer might still be correct. It just hasn't been simplified further. So oftentimes when you get a trig expression like this, using trig identities, you can reduce this down to something smaller. In this case, for my two examples here, we're going to be able to simplify these two expressions to a single trig term. This way, obviously you can't do that for every expression, but I just made it this way so we would know when we were done. So your strategy, since I have secant and cosecant, I can write both of these in terms of sines and cosines. That's generally a good strategy to work with. Just change everybody in terms of sines and cosines. Secant is 1 over cosine, cosecant is 1 over sine. And then what I'm seeing inside these parentheses, if I think of this as over 1, I could combine these two with a common denominator by just multiplying this fraction top and bottom by sine x over sine x. And that's going to give me 1 over sine x minus sine times sine is sine squared x over sine x. I have the same denominator, so this is the same as 1 over cosine times 1 minus sine squared x over sine x. And we just saw that 1 minus sine squared of x could also be the same as cosine squared of x. They're one and the same. So I'm going to use a trig identity and replace 1 minus sine squared with cosine squared. So here I'm just replacing this with an identity. Now this is multiplication, and just like with normal algebra, if you've got cosine x, remember this is cosine times cosine, you can cancel that cosine with one of the cosines there. So you're going to be left with still 1 cosine over sine. Okay, and then another side note here. We discussed how sine of x over cosine of x is the same as tangent of x. That was on a previous video. Well, what's the reciprocal of tangent is cotangent. And if cotangent's the reciprocal of tangent, that means you could write cotangent as cosine x over sine x. So cosine over sine becomes cotangent of x, and as The problem said this reduced down to a single trig term. Now go back to what I said at the beginning, right? Where if you had this answer in a let's say a calculus problem, and this was the answer they had in the back of the book, right? You would totally, that they don't even look the same, right? You would probably think you're wrong when in fact this is the same as this, right? You haven't reduced it down, but it is, there's nothing wrong with that answer. So it's a good practice to be able to take an expression like this and simplify it down. Let's try one more. Cosecant of x over tangent x plus cotangent of x. I'm going to take my strategy again of writing everybody in terms of sines and cosines. Cosecant is 1 over sine of x. Tangent of x is sine x over cosine x. And cotangent we just saw is cosine x over sine x. Now, I'm seeing fractions and I'm seeing a division sign, but remember, you can only flip and multiply when you're dividing one fraction by one fraction. Here I have two fractions, so I can't flip and multiply yet. But what I could do is combine this denominator into a single fraction by getting a common denominator. I'm going to multiply this one top and bottom by sine x, and this one top and bottom by cosine x. And then I'm left with 1 over sine x. Okay, we have the same denominator, right? Cosine times sine, sine times cosine, it's the same. So I have this denominator, I'll write it as sine x cosine x. And what do I have in the numerator? I have sine times sine, which is sine squared x, plus cosine times cosine is cosine squared x. And that is, by the Pythagorean identity, this just equals 1. That is an identity. So we have 1 over sine x divided now by 1 over sine x times cosine x. Now we have a fraction divided by a fraction, so we can flip the bottom fraction and multiply. Of course, when you're multiplying now, you have a common factor of sine x you can cancel out. That leaves me with just cosine x. That's my answer. All right, on the next few videos, we'll look at some other trig identities that you should probably be aware of as you move into calculus.